Hello, I am Alperen and today I will make a short video presentation on the subject of dynamic mechanical analysis with nanoinverter. To make a brief explanation, when a load is applied to a material, it deforms. If the material is an ideally elastic material, the deformation disappears when the load is removed. Elastic deformation occurs in direct proportion to the applied load and without delay. But in some materials, such as polymers, the deformation is nonlinear and takes place with a delay. The opposite of elastic behavior is viscous behavior. In an ideal viscous material, the rate of deformation is directly proportional to the load. Some materials, such as polymers, exhibit both elastic and viscous behavior, and such materials are called viscoelastic materials. DMA measures the viscoelastic properties of materials by using a load motor that increases and decreases at a specified frequency on the materials. The high precision LVDT, here we can see linear variable differ transformer sensor, determines the relative position of the bar on the sample. The dynamic viscoelastic properties of materials can be calculated from the values on the stress and strain waveforms. Principle of dynamic mechanical analysis is a time-varying sinusoidal mechanical stress on the sample. This stress can be carried out as a function of temperature. The DMA can be used to measure the force amplitude, the resulting deformation amplitude, and the phase shift between the force and deformation amplitude. The result of these measurements is the calculation of the complex modulus G of the sample and the determination of tangent alpha. For this, however, the sample must be in the Hookean range, linear elastic the entire time during the mechanical stress. The modulus of elasticity consists of a real part, the storage modulus, and an imaginary part, the loss modulus. The storage modulus describes the part of the mechanical energy that can be stored by the system in a shear over strain experiment. The loss modulus, on the other hand, is a measure of energy dissipated by the material. Solids generally obey the first given case. These show a purely elastic behavior and therefore have no phase shift between the acting force and the resulting deformation. Newtonian liquids represent the second limiting case of purely viscous behavior. Polymers now lie between the two limiting cases and react viscoelastically. The phase shift can assume values in the range 3, here we can see. And the rule here is that the smaller the phase angle, the stronger the polymer under investigation. Furthermore, temperature dependency can be determined so that when the temperature increases, the viscous force elongation for all the part range proportion the polymer increases and the phase angle increases according to shifts to the larger values. Dynamic mechanical analysis is used to determine the temperature and frequency dependencies of the storage over loss modulus and the loss factor. In this diagram, we can see the typical DMA thermogram for an amorphous thermoplastic, which is polycarbonate, measured in dual cantilever deformation model with a measurement frequency of 1 Hz and a heating rate of 2K over minute. Nanoinverter is a device used to measure the nanoscale mechanical properties of the material surfaces. This device is known as a hardness tester and applies an inverter with a 1 or more micron size to surface of the material in the controlled manner. This inverter, while applying a microscopic force, gives marks or deformation on the surface of the material. The nanoinverter is used to measure the mechanical properties of the material such as elastic modulus, hardness, flexibility, yield strength, fatigue resistance, and surface properties. It has a wide variety of nips such as Berkovich, cube corner, Vickers, and knob. Here we can see the Berkovich tip. It's a GIF, but I can't play it, so let's continue. Let's try again. Okay. Now it's work, I guess, yes. The working principle of the nanoinverter is based on measuring the force exerted by the inverter on the material surface and the depth of the trace. The relationship between the force and indentation depth is analyzed by mathematical models used to calculate the mechanical properties of the material. In this way, properties of the material such as elastic behavior, plastic deformation behavior, surface hardness, and modulus of elasticity can be determined. Continuous stiffness measurement (CSM) stands for continuous hardness measurement. This term is a technique used in material characterization. CSM is used to continuously measure the elastic modulus or hardness value of the material. CSM is a measurement technique often used with materials testing equipment. In this technique, a force is applied to the material using a force stability control, and the amount of displacement or deformation of the material against this force is measured. This measurement is made continuously to monitor the elastic behavior of the material and obtain parameters such as elastic modulus or hardness value. By combining DMA with nanoindentation, it's possible to obtain a comprehensive understanding of the viscoelastic behavior of the material at both macroscopic and microscopic levels. DMA provides information about the material's bulk viscoelastic response, while nanoindentation allows for the assessment of mechanical properties at site-specific location or features on the material's surface. The simultaneous application of DMA and nanoindenter opens up diverse possibilities for the comprehensive characterizations of materials on different length scales and enables detailed insights into their mechanical properties. Viscoelasticity can be studied using DMA during nanoindentation. By applying controlled oscillatory stress, the resulting strain can easily be measured. An elastic material will have stress and strain in phase, while a viscose elastic material will have strain lagging stress. In many applications during quality control and R&D, it's important to reliably test this behavior. We can see from this diagram the complex modulus as a function of frequency is determined by dynamic nanoindentation and DMA. This combined, which is DMA with nanoindentation, approach can be valuable in various fields, including material science, polymer research, thin films, coatings, and biomaterials. It enables researchers to obtain a more detailed characterization of the mechanical properties of materials and gain insights into their viscoelastic behavior across different length scales. For example, polymer coatings like that found on solar panels and medical devices need to be studied by DMA nanoindentation to understand this transition between viscose and elastic properties. The behavior of polymers is greatly affected by time and temperature, which can greatly affect the long-term longevity of the device if the properties are not well understood. These results will be used to better understand the life cycle of the polymer coating, among others. And thank you for listening me. Danke für Ihre Aufmerksamkeit.